Maybe before I start my talk, if there are any questions, outstanding questions from yesterday, I can take them now, and then we can go on to resolution of the information paradox. Are there any questions that people had from yesterday that they did not get a chance to ask?
So one thing you didn't really mention is fuzzballs.
Oh yeah.
So how does that fit with this? So part of the philosophy there is that a given microstate may not look smooth.
Right. So I think that fuzzballs are, well, I think that if you give up on the smoothness of the interior, you're led to firewalls. Fuzzballs are I think fuzzballs are an attempt to find some kind of intermediate path, which I think doesn't really exist. So the idea in fuzzballs is that just like, you know, the idea in fuzzballs is that you once again try and give up the entanglement between the inside and the outside. But the people who do fuzzballs want to say that doesn't lead to a firewall somehow, but leads to something where some high energy observer still sees a smooth interior, but some low energy observer sees these excitations, and that's this idea called fuzzball complementarity. To be honest, I don't understand how any of that is consistent. So my impression is that I think there are really two significant options, and one of them is that black holes have empty and smooth interiors, and the other is that generic states in black holes have firewalls. I think this idea of fuzzball complementarity, which is that some observers who are high energy observers see something which is smooth, whereas if you're measuring the black hole at low energies, you see something that's not. I don't think that makes sense, and one of the reasons I think it doesn't make sense is what I discussed, is what we were discussing also during Masaki's talk, which is that if you look at typical states from the microcanonical ensemble and you pick them using the hard measures, and you look at the variance of correlation functions in these states, the variance is extremely small. So I think to argue that these typical states can be represented somehow by distinct microstate geometries, I think is in contradiction with the fact that two typical states look identical almost to almost all low point energy correlation functions. So I think for this reason, the idea that there are these different geometries that represent microstates, I think I don't think is correct. But we could talk more if you like. But my impression is that the fuzzballs are some attempt to try find some middle way, which I think doesn't really exist. But I mean, also there are many different versions of the fuzzball proposal. So there are different people who say different things. There are some people who really want to find three-charge solutions and count microstate geometries. There are some people who want to say that these maybe the geometries don't exist, but there's some in principle setting in which the black hole interior is not smooth, and so I think there are different proposals, and we can discuss them in detail. But that's the reason I didn't mention them as yet.
Yeah, but could a potential answer be that yes, there are these fuzzball solutions, but they're such a small fraction of the actual?
That could certainly be an answer. So if there are fuzzball solutions and in fact it is true that the solutions people have found are exponentially small compared to the full Hilbert space, and so if you have these solutions and they're an exponentially small fraction of the Hilbert space, then you wouldn't see them in any analysis of generic states. If you take a generic state, these solutions don't contribute at all. So if there are solutions in the exponentially small subset, then that's fine, but they don't contribute to the analysis of generic states. Okay, so let me just remind you a little bit. Let me remind you what I said yesterday. Yesterday I tried to describe the progression of the information paradox from these old questions of how evaporation is consistent with unitarity. And then to these more recent developments about strong subadditivity, and then what I call the modern information paradox. And as I said, the modern information paradox was the modern information paradox was really an existence question of operators in the CFT that were dual to bulk modes. So I think that this is a rather robust question, something that you can phrase precisely. It's a question of whether the CFT contains operators that can describe local bulk degrees of freedom. And I tried to explain how you could argue just based on very general properties of these local bulk degrees of freedom and general properties of the CFT that it appears that these operators don't exist. And today I'll try and describe some resolutions to them. So I think that just to summarize what I'm about to say, I think that I said yesterday that the old information paradox can be resolved by recognizing that there are limits on bulk locality. And what I would like to propose today is that these modern versions of the information paradox can be resolved if one recognizes that the bulk to boundary correspondence should be phrased, in the neighborhood of a given microstate in the CFT Hilbert space. So the statement is that if you're in a given black hole microstate and you're performing experiments, you're an observer who falls into that given black hole microstate and you perform some set of experiments, then the degrees of freedom that you use, the operators that you use to describe, excitations about that microstate may depend on the state of the black hole, and this is what we call state dependence. And as I'll try and show you, this resolves all the paradoxes that I described yesterday. So this is the essence of the resolution, and I'll try and flesh it out in the course of this talk. I don't usually do this, but just to say, the way I want to go about this is I first want to introduce this resolution in a spin chain toy model. So in fact, I'm going to go back to the strong subadditivity paradox I described yesterday and show you how state dependence works in a toy model where you model black hole evaporation by a spin chain, just because it's pedagogically useful, and then I'll generalize this resolution more broadly to the CFT and talk about applications. I don't have a table of contents here. Okay, sorry, I forgot to put a table of contents slide. Let me just tell you how I plan to go about this. So I'll talk about the spin chain, as I said, and then I'll try and generalize that to talking about the CFT and try and generalize this proposal that we have for constructing black hole interior operators to the CFT more broadly. And then I want to describe some applications of this proposal. In particular, I'd like to discuss an application of this proposal to the ER equals CPR proposal of Muddelson and Susskind, and try and explain how our proposal for constructing the interior gives you a precise version of that. I want to talk a little bit about what the significance of state dependence is in terms of what it means for the classical limit of AdS CFT. And finally, I want to describe some open questions which I didn't discuss yesterday, and mention some speculative ideas. But I'll try and do that in the last 10 or 15 minutes. So let me start by talking about the spin chain. Just to say, the way, as I said, I'll start by describing a toy model and resolving these paradoxes in a toy model. So the spin chain toy model is a very simple model. You just take n spin half states, and of course, if you have a system of n such spins, then the system, each spin is a two-state system, and so there are 2 to the n total states in the Hilbert space. So you can write these states in some binary notation. This is when all the spins are down. That's 0. When all except the last one are down, the last one is up. That's the state 1, and so on. So you can write the states in binary notation as states from 0 to 2 to the n minus 1. And now I want to consider a generic state in this model. Okay, so this is a very simplified model. There's no CFT, no dynamics. And in this model, I have, I take some generic pure state, which I can write as a linear combination of these states, and I can pick these coefficients AI using the Haar measure. And of course, they have to be correctly normalized so that AI squared, sum of AI squared is 1. Okay. And the model of Hawking evaporation I'll have in this picture is basically just to break off the spins one by one. Okay, so my model of Hawking evaporation is that you have the spin chain, and the spin chain is just breaking into parts. One spin goes off, and then after some time another spin goes off, and so on. Okay, so this is the model of Hawking evaporation, a simple model. So here's how you picture it. Here's a spin chain which has 7 spins, and here's a spin chain. This is the full black hole. And at the first step, it breaks up into something which is the remaining black hole, and this is this subsystem B, which was this Hawking particle that was being emitted, and this is the subsystem A, which consists of all the Hawking radiation that's been emitted so far. After some time, one more spin goes and joins this, so there are only 3 spins left in the black hole. This is the spin B prime, which is being emitted now, and now this old spin went and joined A, so this is what A is. Notice that the initial spin chain was in a superposition of this state, plus this state, plus this state, and that means that A is in a mixed state. Okay? Both A and B are in mixed states. So if you have if the initial state is a superposition of this plus this plus this, then at each step you get a superposition of this plus this plus this. Next step you get a superposition of this plus this plus this, and this is how evaporation goes. Okay? So this is a very simple model, and I hope the model is clear. Is the model clear? Okay. Very good. So now I think that one of the points I want to make is that from an information theoretic perspective, this model is not very different. Of course, the CFT has dynamics, and I'll talk about that in a second. But it's very clear, first of all, how to realize these systems A and B. So just to remind you once again, A was you had a black hole, and B was some particle that was being emitted, and A was all the over radiation. A is all the old radiation, B is the particle that's being emitted, and C was its partner inside the black hole. Okay, so this is just to remind you of notation from yesterday. And it's very clear how to realize A and B in this model. In fact, I already did so in the previous slide. It's also by the way clear that these systems A and B have the right properties that we want. So for example, if you consider this guy B, which is the spin that's being emitted, then in fact it's clear, as I showed you previously, that the spin that's being emitted is not in a pure state. It's not in a pure state because the initial state is a superposition of different possibilities for the spin, and therefore you have to describe the state of the spin in terms of a density matrix, and it's easy to see using the same arguments as Page had, that if you look at some typical state, okay, of this kind, and you look at the density matrix of each emitted spin, so you look at any particular spin and look at its density matrix, the density matrix is very close to the identity, plus some corrections which are exponentially small. This is the e to the minus s by 2 factor that I had yesterday. So it's very easy to verify that this is the case. It's also easy to verify that if you look at the set of emitted spins, so if you take the spin chain and you break it up into 2 parts, and you look at all the spins that have been emitted, and you look at the entanglement entropy of that set, then that set has an entanglement entropy that goes up. It goes up to n by 2 and then comes down. Okay. So it's n by 2 in units. This is in units of log 2. But the entanglement entropy of this set A goes up and comes down. And once you cross the Page time, which in this toy model is just when half the spin chain has evaporated, the entanglement entropy starts coming down. And it's very easy to take a generic pure state and you can verify these properties of A and B. Okay, so A and B are very clearly realized in this model. Another question is where the infalling quanta, which are these guys C, okay, which are the partners of the B's. So can you realize also these infalling quanta in the spin chain? That's the question. And you might
what was the initial state? Is it superposition
of
all possible states?
It's a superposition of all possible states. You pick using the Harbinger. Question is where the infalling quanta in the spin chain. So this is the question. This, by the way, was also the question that we had yesterday. What were the modes that describe the infalling degrees of freedom? So what do we want for the infalling quanta? It's not obvious what the infalling quanta are. It's clear what the outgoing quanta are, but it's not clear what the infalling quanta are. What you want really is you want some degrees of freedom that obey the same SU2 algebra, because you want the infalling quanta to also be spins. So you want some degrees of freedom that obey the same SU2 algebra as the ordinary spin operators do. Okay. Second, you want that this C qubit is perfectly correlated with the B qubit. So if you describe the state of the B qubit with some S operator, then you want the C qubit to be perfectly correlated or perfectly anti-correlated with the B qubit. Okay. That's the statement that these spins are being emitted in singlets. And you also want these infalling quanta to be effectively independent degrees of freedom. So because you want them to be effectively independent degrees of freedom, you want them to commute with the ordinary spins. So the question of where are the infalling quanta can be phrased just as we had in the CFT as a question of finding operators in the spin chain that have this property. That have the property, first of all, that they represent by themselves some spin algebra, that they are perfectly anti-correlated with the ordinary spins that you're seeing, and they commute with the ordinary spins. So it's a question of finding operators that do this, and if you can find operators that do this, whatever method you have of finding them, then you can declare that these are the operators that describe the infalling quanta. Okay. Let me remind you that this is very similar in spirit to the problem that we had yesterday. Yesterday I said that we wanted to find these operators in the CFT, and they obey some algebra which was the Heisenberg algebra, the simple harmonic oscillator algebra, which wasn't the SU2 algebra, but that's because those represented creation and annihilation operators. They also commuted with the ordinary degrees of freedom, so the tilde operators commuted with the ordinary operators, which is what we want for the spins, and they had a correlation with the ordinary operators. In the CFT situation, we had all these factors of e to the minus beta and so on, which don't occur here in the spin chain because I haven't put in any temperature. But in spirit, it's the same kind of problem. You want some operators which have the right algebra, and they have the right, they have the right commutators with themselves. They commute with the ordinary degrees of freedom, and they have the correct 2-point correlators with the ordinary degrees of freedom. So in spirit, this is very similar to the problem that we had yesterday. Okay. So now I think the key realization, and this is the important realization, is that in fact these conditions I put in these S tilde operators do not have to hold as operator equations. Okay, and this is I think the most important point I want to make here. That I said that these tilde operators need to commute with the ordinary operators and they need to be correlated, but you don't want them to commute as operators. Rather, you want these equations to hold within correlation functions, and you want them to hold not within arbitrarily high point correlation functions, but within correlation functions with some cutoff on the number of insertions. So more precisely, what you want to say is that you have a spin chain and you don't have infinite accuracy. So you can't measure all possible correlation functions in the spin chain, but I'm going to allow you to measure some correlators of ordinary operators with some limit, capital K, on the total number of insertions. So the spin chain has a capital N number of spins, but I won't let you measure all spins simultaneously. You can measure any subset K that you like. You can choose your subset. You can measure 2-point or 3-point correlators between any two spins, but you're not allowed to measure arbitrarily high point correlators. So there's a limit on the accuracy that you have, and correspondingly, the relations you wanted for the tildes and these guys are that you should have the tildes and the ordinary spins being correlated within correlation functions. So it shouldn't be that the tilde acts in a state exactly the way an ordinary spin does, but rather that if you put up to k insertions, then the tildes are correlated with the spins. So this relation with k plus 2 insertions, with at most k plus 2 insertions, gives you a minus delta ij for these guys and the usual correlation function. And you want the ordinary guys and the tildes to commute, but to commute within correlation functions. Not to commute as operators, but to commute within correlation functions. So this is the most important limitation I'm going to put in these operators, which is that you want them to have the correct properties within correlators and not as operators. And this is, I think, the essence of the point that I want to make in this talk. So are there any questions here about this point? Yeah.
Why do we have, why is the accuracy limit by the cutoff on the number of
So that's a physical input that I'm putting. I'm saying that you just like if you have an observer in AdS CFT, because observer does not have the ability to measure arbitrarily high point correlation functions. So which is what we discussed at the end of yesterday's talk. You don't want the bulk observer to be able to measure an n squared point correlator. And if you do, then you don't at least want some bulk effective field theory description for that observer. So in the same way, I'm putting a cutoff here on the number of spins an observer can measure. And I'm saying that I will describe the infalling quanta in a coarse grain description where my definition of coarse grain is that you consider correlators with at most k insertions. So the claim is if you consider correlators with too many insertions, then there is no description of the infalling quanta. But there is a description if you coarse grain the dynamics a little bit. And it's the same as what happens in the bulk. The statement is that if you want a description in terms of some nice geometry, which has some observer and somebody outside and somebody inside, then such a description exists, provided you measure, correlation functions in the interior which do not scale with the central charge, where the number of insertions does not scale with the central charge. So at the end of yesterday's talk, we had some discussion of, how the large n expansion would break down if you put too many insertions in the bulk. And so there's a physical reason for this cutoff.
You want to measure it only on psi?
I want to measure it only on psi. That's right. So you have some observer who you can take whatever state you like, psi. And then I'll tailor my observer.
So even with small number of insertion, you don't want it to be valid on low-lying states, for example.
What are low-lying states? I start with some state psi, and the small number of insertions, tell you what experiments this observer can do. So the observer is falling into some state of the system which is psi, and then he can measure these correlators in that state psi. Yeah.
Do you want these to be true up to 1/n corrections?
In the spin chain model, it'll be true exactly, but in general, you can make them from 1/n corrections. In the spin chain model, I'll make them true exactly, but that's because it's a toy model. In general, I want them to be true up to 1/n corrections. In this model doesn't really have any meaningful 1/n except for the size of the input space. Okay, so now I'm going to define the mirror operators because the challenge is to find any such operators that do the job. And here's the definition. It's actually not a simple definition. And it's quite similar to what I'll do in the CFT. And it's as follows. Let me define the mirror operators using a set of linear equations. Okay. And what are the set of linear equations? The set of linear equations are as follows. Let me take S tilde and let me define its action on the state psi to be basically negative of the action of the ordinary spin operator on psi. So by the way, J is the index that goes from 1 to n, and A goes to x, y, z. So I define the action of S tilde on psi to be this, and then I define the action of S tilde on an excitation of psi by up to, by p ordinary operators, as basically saying that S tilde floats to the right. So this gives you a lean, and of course once S tilde is here, then I know how it acts on psi by the first equation. So these two equations, recursively specify the action of S tilde on psi and on any descendant of psi obtained by acting with up to k insertions. Okay, so this is a set of linear equations that specifies for you what this S tilde is. So it's a set, and I'm going to use this to define S tilde. Now you might worry that these equations don't have a solution, but in fact some simple counting tells you they do have a solution. And yeah.
Sorry, isn't the first equation in contradiction with them being SU2 generators?
No. Why is it in contradiction with being the SU2 generators?
If you put minus signs in front of all three.
Oh, right. Good. Good. I might need to be careful about the minus signs and well, let's see. Let me think one second. So you're saying that they'll obey an SU2 algebra with a one second. I think not actually for the just give me 1 minute, but I think it's not. I think that it's because just give me 1 minute. Let me go to the next slide and then I can explain it. But I think it's consistent, and the reason it's consistent is as follows. I think you start with S tilde x, S tilde y, psi, okay, and that is you get a minus sign once, which is this becomes sy psi, so minus S tilde x psi, okay. And then you get another minus sign, so sy sx psi. So you okay, so this gives you, and then you work up the other thing. You may be right that maybe the way I define them, I may have let's see, S tilde y, S tilde x psi is would give you S right. So I think you're right that this might give you yeah, this might give you Sx sy psi. So I think that if you compute the commutator, you'll get the commutator of. So I think it's okay, because I think if you compute the commutator of these two guys, you'll get what you'll find will be S tilde y, S tilde x on psi is Sx Sy on psi. So that you flip the sign because of what I said here. But this is xy, it's I as z on psi, and that's actually equal to minus I S tilde z on psi. So I think it's okay. You see, let's use these equations. Let's act with S tilde x and S tilde y. So by the rule here, S tilde y gives you minus of sy. That's the first rule here. Okay. Now S tilde x acting on sy, you see by the second rule here, S tilde goes to the right. So you get one more minus sign, so you get sy sx. Here you get S tilde y, S tilde x, so you get sx sy. So this commutator S tilde y, S tilde x is the same as the ordinary commutator, but with the sign flip. That xy gives you sz, but sz is the same as minus I tilde sz by the first rule, and that's the correct commutator. So I think it's okay. So you can use these rules as I just showed to basically recursively specify the action of the S tilde in any state, and they obey the right algebra as we just checked. Okay. But notice that you might have thought that there is no solution, but there is a solution, and that's because S tilde is a matrix in a 2 to the n dimensional Hilbert space. So it's a 2 to the n cross 2 to the n dimensional matrix. And if you can count the number of constraints I've put in it, the number of linear equations I've specified, and the number of linear equations is easy to count is this. It's sum of, and that's because you can choose n minus j of these insertions. Sorry, k minus j of these insertions to be. You can choose some number of insertions to be the identity, and then you can pick j of these insertions to be one of the sigma matrices. So if you want up to k insertions, if you're allowed to act with up to k sigma matrices in a state, you can check that this is the number of descendants that you produce. And this number is much smaller than 2 to the n, provided you keep k much smaller than n. Provided you keep k much smaller than n, this number is much smaller than 2 to the n. And if you take a generic initial state, for all except some measure 0 set of initial states, these vectors that you get are all linearly independent. Okay? And therefore, as long as d is smaller than 2 to the n, and you start with a generic initial state, the set of linear equations that I showed you does have a solution. So you're guaranteed to get a solution just by rules of ordinary linear algebra for any such, for this setup of linear equations. Okay. And as I said, this equation does satisfy all the rules that you want. Yeah.
So if I consider the n is the relatively small n, then
Oh, if you consider relatively small n, then this just and then you have to take k to be also very small. Or the description
okay,
makes that.
the solution may not exist.
Well, if you take n to be 2 or 3, then the solution may not exist. But I think that
Absolutely.
the important point here is that you want to do this you want to play this game in a big Hilbert space.
Yeah, of course.
In the CFT you have a big Hilbert space,
Yeah,
and
that's
you learn to measure. Right. So you have to have a hierarchy in the system, which is the hierarchy between the number of observations you're allowed to make and the size of the full system. So this hierarchy is very important for getting this effective distribution. Unless there's a hierarchy, it doesn't work. And in the CFT, you do have such a hierarchy.
Yeah,
Because you're
I'm just a kind of explicit manipulation to write down the solution.
Let me show you some explicit. I'll actually do this in Mathematica. So give me a second. Good. Okay, thank you. I anticipated that question a little bit, so I'll show you some demonstration of this. Okay, good. So let me just check that. Let's just check that it satisfies the equations we wanted. Of course, you can act with this, and you can use the rules that we have. Make S tilde become S, and you get, of course, delta ij, because S A S B, but just in a generic state, two spins happen to be correlated. They happen to have the correct correlation function. It's delta ij, delta ib, and you can check that this commutator also works. So the way the commutator works is the rule was that the S tilde always flows to the right. So whatever ordering you have here, the S tilde flows to the right. And you can check that the commutator is 0, but it's 0 only on the state and in descendants of the state. It's not 0 as an operator. Okay. So you can check that these linear equations, by construction, will be the right operators.
What does the commutator as an operator equation give you anything nice?
The commutator as an operator equation does not give you anything nice. The commutator is some horrible operator which happens to have the property that it vanishes about the state. It's something which is. So there's some non-zero commutator, but the poor observer who can only measure k spins can't see this. So I'll give you an explicit numerical example in a couple of slides. Okay. So just give me 1 minute for that. So let me just point out that let me just go back to the resolution of the strong subadditivity paradox I pointed out. So the point, as I said yesterday, was that if you looked at this A, B, and C which I erased, which was the old radiation in the particle just emitted in the particle inside. These did not live in 3 independent different Hilbert spaces. And the reason for that here is very clear. No, there is actually no operator by Schu's lemma, just by trivial reasoning, there is no operator that actually happens to commute with all operators. Okay, there is no operator which has this property. And therefore, necessarily true that this operator S tilde that we define is actually acting on the same degrees of freedom that the ordinary spins are acting on. Okay. So there is actually no operator which has the property that it commutes with all the ordinary spin operators in the spin chain, and therefore it is acting on the same degree of freedom. But as we discussed, this commutator vanishes effectively. So it looks like it's describing an independent degree of freedom, but it's not really describing an independent degree of freedom. It's somehow acting in a scrambled manner. So this is what I said yesterday. The inside of the black hole is a scrambled version of the outside. So it's scrambled in some clever way so that some observer doing some simple experiments inside and outside can't detect that they're actually manipulating the same degrees of freedom, but in fact they are secretly manipulating the same degrees of freedom, and this is a concrete example of that. Okay, so there are a couple of questions already, so let me show you a demonstration of this. Let's see. So this is a spin chain in which I have only 5 spins. Okay, so you can